So sorry about that. Thank you for reminding me. I always appreciate when people remind me. So what we have here is basically we're laying out here the different functional groups that we're going to study here in chapter 10. And they are all either derivatives of carboxylic acids or closely related by structure and reactivity to carboxylic acids. And really, I think these four types of compounds all belong together in that sense. And as I said, you could also throw in acid chlorides and acid anhydrides, which are other functional groups that we've discussed. We'll probably see those a few times in this chapter also. But in this chapter, we're going to be concerned about, what we are always concerned about in organic chemistry: structure, reactivity, and where appropriate, mechanism. But mainly here, structure and reactivity. And the reason this matters is with the possible exception again of nitriles, but certainly these three functional groups show up a ton in living systems. And so there's no complete understanding of the Krebs cycle or of glycolysis or of polypeptides unless we understand how these functional groups behave. So that's basically the idea behind it. And it's not for nothing that we're going to finally look at the amide functional group, for instance, in this chapter. Well, lo and behold, as you probably already know, what are peptide bonds in proteins? Peptide bonds are amide functional groups, period, full stop. They're one and the same thing. So I think it's very timely to cover these functional groups before we get to chapter 17, which is our last chapter, the one on polypeptides and amino acids and all that stuff. So again, just a reminder that certainly the inductive effect and resonance still affect the structure and reactivity of all of these, but especially in the cases of carboxylic acids and esters and amides, what we find is that in addition to the two resonance forms that we've discussed, there's a third one that plays a role in the structures of these compounds, which now takes some of that partial plus charge off of the carbon and puts it on the oxygen. So that means that carboxylic acids, and you could draw similar resonance forms, by the way, for amides and esters, but it means that these three types of compounds are less reactive to nucleophiles than aldehydes and ketones are. They still react, but less readily, not as quickly. And so I think we'll see that when we start getting into some of the reactions, which I think we will already do today. Certainly, I want to clarify how to make carboxylic acids. But chapter 11 is kind of lengthy. We've had some shorter chapters recently. This one's kind of lengthy. I believe we're splitting it up into 3 parts, and I am totally okay with that. That will still leave us 2 class days for chapter 17. And as with so many things, I am in no mood to rush through this too quickly. So if we can, let's see, aldehyde and ketone also don't undergo SN1 or SN2, right? Because they're the sp2 hybridized carbons. That's exactly right. So that's why, and you'll find the same thing with aromatic carbons and vinylic carbons, because those are also sp2 hybridized. So we do need the carbons to be sp3 hybridized in order to undergo these straight nucleophilic substitution reactions. That being said, compounds like carboxylic acids and esters and amides do undergo nucleophilic substitution reactions, just they are neither SN1 nor SN2. And like I said, if I have a ton of time and we're all bored, maybe I'll go through an easier one of those mechanisms, but I don't expect that you'll be responsible for these mechanisms. We did some mechanisms in the chapter on aldehydes and ketones. We did some that were very short and less complicated conceptually. But these types of reactions tend to be very steppy. And so I certainly am not going to go there right away. And it's not something I'm going to expect you to be responsible for. Good. So all that being said, what about properties of carboxylic acids and nomenclature of carboxylic acids? I think I can leave nomenclature for you to work on at your own pace on your own. There are certainly some problems that involve nomenclature of carboxylic acids in the OWL assignments, But generally, the main thing is it's this ending, ic acid, that gets used for carboxylic acids. That being said, the smallest carboxylic acids, the smallest one is, of course, formic acid, where R is a hydrogen. And you could call it methanoic acid, methanoic acid, but no one actually calls it that. Everyone calls it formic acid. That's the same form as in formaldehyde, by the way. So it kind of makes sense. That comes from the same root. But even formaldehyde could be called methanal, but no one calls it that. Likewise, acetic acid, where R is a methyl group, could be called ethanoic acid, just as acetaldehyde could be called ethanal, but no one uses those names, not anymore, and at least not in general. People will kind of roll their eyes at you if you use names like that. So those are usually called formic acid and acetic acid. The 3-carbon carboxylic acid is called, you can call that one propanoic acid, which would be the IUPAC name. It's also called propionic acid. Both names are acceptable. The 4-carbon carboxylic acid, just to give you some examples, I don't care if you memorize these, but the 4-carbon carboxylic acid could be called butanoic acid, butanoic acid, or it's also called butyric acid, butyric. And it's called that, it's related, it's a name related to butter because butyric acid is found in rancid butter. So you can take a guess as to what these things smell like. It so happens that the 6-carbon carboxylic acid, I don't care if you memorize these trivial names, they're not used as much any longer. Certainly you could call that hexanoic acid, hexane, hexanoic acid. But the trivial name for hexanoic acid is caproic acid, CAPROIC. And that comes from the same root as Capricorn the goat because it smells like billy goats. So there you are. Carboxylic acids tend to have unpleasant odors, at least until they get large enough that they're no longer volatile, they're not giving off molecules into the air, and so you can no longer smell them. And by the time you get to, 12 or 15 carbons, you can't really smell them too well any longer. Good. So what about other properties of carboxylic acids? Well, and also these other derivatives. Well, we've said already that the carbonyl carbons here are going to be sp2 hybridized. No surprise there. Same thing in amides. That's also an sp2 hybridized carbon. Same thing in esters, also sp2 hybridized. Same thing in nitriles, just kidding. Gotcha. Those are, of course, sp hybridized. You have to have sp hybridization in order to accommodate that triple bond. So just like in alkynes, the carbon in a nitrile is sp hybridized, as is the nitrogen, by the way, also sp hybridized. So, but sp2 hybridization is pretty common for carboxylic acids and their derivatives. We already went over how they're less reactive towards nucleophiles than aldehydes and ketones, and we explained why that is. Another feature of carboxylic acids that's kind of cool is, especially if R is relatively small, 1, 2, 3, 4, maybe 5 carbons, something like this. These things tend to dimerize, at least in the pure liquid state and in the gas phase. And they do so by hydrogen bonding. And it's not that hard to understand why that is, I don't think. I just want to be careful to draw this right. We're going to need another hydrogen bond over here. Yep, this will work, however, barely. I know I could have made that look better. I see how to do it. Let me just make that prettier. Now what I need to do is go like this. There we go. Then the carbon will go here. This will be single bond OH, double bond O over here, and another R group over here. So they tend to form dimers like this by hydrogen bonding. And that's very typical for carboxylic acids. The only time they're not going to do that is if R is really stupidly huge. You know, if this is 15, 20, 30 carbons, if this is some fatty acid, for example, then the molecules are not going to be able to approach each other closely enough to make this happen. But certainly small to medium-sized carboxylic acids can undergo this type of intramolecular hydrogen bonding. And so as a result, we've heard this same song many times this term. That means that you need to put in extra energy in the form of heat to first of all separate these molecules from each other, and then to get them to go from the liquid state into the gas state. So carboxylic acids tend to have very high boiling points, at least compared to, say, alkanes or even alcohols of similar molecular weight, because you have to break apart these dimers. But again, just a reminder, when you boil something, you are not breaking covalent bonds. It's not a chemical reaction. It's a physical process. And so breaking these hydrogen bonds is not the same thing as breaking covalent bonds, totally different critters. What is comparison to aldehyde of what? Boiling point? I would say carboxylic acids are certainly more polar than aldehydes. And aldehydes are not able to undergo hydrogen bond donation because they don't have an OH bond, right? You have to have an OH bond or an NH bond in order for something to be a hydrogen bond donor as well as a hydrogen bond acceptor. So I would expect an aldehyde and a carboxylic acid, if they have similar molecular weights, I'd again expect the carboxylic acid to have a higher boiling point. That would be what I would expect anyway. And I certainly would be fine with all of you expecting the same thing. Let's see. And I already went over their odors. Good. So any questions then so far? I think from this we're ready to go on and consider about carboxylic acids being acidic. Shocker of shockers, right? Good. Everything other than that making sense so far. And I'll just mention, by the way, I don't know that this is really going to affect you guys, it better not, but in case you're curious, on Friday morning to about 1 p.m., I'm giving online exams in my other classes, my Chem 227 classes. Those should be completely done by the time I have to leave home, and I should make it to class on time. I think the whole thing will be totally seamless from your perspective. I don't think you'll notice anything different. But, you know, just in case there's some sort of act of God or some weird thing happens, just so you know, I won't actually be on campus before your class, but I should make it here on time. Actually, I live closer to the Bush Library. Do I live closer to here than the Chem? I don't know. I think this is roughly in between. It's pretty much the same drive. So everything should go just as normal on Friday for us. Let's see. And on Monday, when we have our exam, of course, I'll teach those two classes, and then I'll scurry home in order to be ready for your exam that day. So, which I haven't even started on. No idea how many questions there will be, but we will get that done as well. Good. So what about acidity of carboxylic acids? Well, for most carboxylic acids, and I don't really care if you memorize particular ones, but I think in general, if R is something ordinary, you know, just an alkyl group, in general, I think we can expect these to have pKa values round and about 4, give or take. So I think that's a reasonable place to put it, approximately in that area. And remember, by the strangest coincidence, by the way, I said exactly the same thing in my 227 classes this morning, but it is only just a coincidence. Remember that in order to understand relative acidities, you have to think about the conjugate base of the species in question. You have to. If you refuse to think about conjugate bases, and especially if you don't really know what a conjugate base is and how to come up with its structure, you're going to have real trouble understanding relative acidities, which we'll get into next. What is the reason aldehyde doesn't undergo hydrogen bonding? Well, aldehydes can be hydrogen bond acceptors because they have that carbonyl oxygen, but aldehydes don't have an OH bond in them, right? You need to have hydrogen directly attached to oxygen or nitrogen in order for it to undergo hydrogen bonding. And we don't have that here. So aldehydes can't donate hydrogen bonds. You got a CH bond, not an OH bond. So that's why. Therefore, I would also say they're quite a bit less, they're still pretty polar, quite a bit less polar than carboxylic acids. So aldehydes can accept hydrogen bonds of the carbonyl oxygen, but they can't donate hydrogen bonds. So in some sense, carboxylic acids are a little bit more like alcohols because they can both donate and accept. Or molecules of carboxylic acids and alcohols can both donate and accept hydrogen bonds. So anyway, let's then compare this to, let's say, an alcohol, and we'll even make it of the same number of carbons as the carboxylic acid, just so we're comparing apples to apples. And as you may recall, if you wanted to put a rough pKa value on a typical run-of-the-mill aliphatic alcohol like this, I think you're going to be rounding about the 16, 17, 18 area, something like that. That'd be a reasonable place to put it. And alcohols can act as acids. Actually, alcohols are amphoteric, just like water and ammonia are. Amphoteric means they can act as either acids or bases. So certainly the alcohol can act as a base and pick up a proton from a strong acid, and then you get the conjugate acid of the alcohol. This one would be RCH2OH2+. It's basically very similar to H3O+. But alcohols can also act as acids and give up H+, and the species that you get then in the end is what we call an alkoxide ion. It's the conjugate base of the alcohol. And again, as I said, you have to think about conjugate bases in order to have any shot at understanding relative acidities. So that would be the conjugate base of the alcohol. And you can see there's a real tremendous difference in terms of acidity in the conjugate acids. Remember that the pKa scale is logarithmic. So each time you move up or down by 1 unit in the pKa scale, it's a factor of 10. So to say that this pKa is in the 16 or 17 range, and this is like 4 or 5, you're talking roughly a factor of 12 orders of magnitude, give or take. In other words, carboxylic acids in general are about 1 trillion times as acidic as similar molecular weight alcohols are. So it's not close. So there needs to be a reason for that. And I don't think the reason will come as any surprise. I already told you, by the way, it's sort of, oh, what's the word I'm looking for? A cynical way of putting it, but it's unfortunately true. In general, if you're asked pretty much any question in organic chemistry, if you answer resonance or the inductive effect, there's like a 75% chance that it will be at least one of those. And I would say really both the inductive effect and resonance come into play here, but let's consider the difference between these two conjugate bases. And what I hope to convince you of is this conjugate base is significantly more stable than the conjugate base of an alcohol, the alkoxide ion. And this one's going to be less stable. This one's going to be higher energy. The other one is going to be lower energy, the more stable one. Or if stable isn't working for you, I don't mind if you say this species is happier and this species is less happy. I'm totally fine with you thinking about it that way. But there's got to be a good reason for it. And I think it's one we can understand. And sure, we could talk about the inductive effect. You know, this carbon over here has 2 electronegative oxygen atoms sucking electron density away, and that helps to stabilize this oxygen with the minus charge, whereas this carbon is only the 1 oxygen. So there's fewer stabilizing atoms attached to this carbon than attached to this one. This oxygen with a minus charge has a whole lot of electron density on it. And so this oxygen being so electronegative helps to withdraw some of that electron density. Remember, all electrons are negatively charged and like charges repel. So anything we can do to spread out that minus charge makes the system more stable, other things being equal, because you don't have all the electrons as close to one another and repelling each other quite as much. Instead, you're letting them spread out over more 3-dimensional space. And so it's a more stable situation. But it's not just the inductive effect. We can also invoke resonance here. Recall that carboxylate ions, which is what we call species like this, that are the conjugate bases of carboxylic acids. So carboxylate ions are resonance stabilized species. I could just as easily, without moving any of the atoms, I could just as easily have put the electrons in like this, so that the minus charge is on the other oxygen. And in fact, you could even argue that there's yet a third resonance form that has minus charges in both oxygens and a plus charge in carbon. That one's going to be very minor. I certainly think these two are going to be the main contributing resonance structures to the overall hybrid. And so what that means is that the minus charge is delocalized. Some of it is on this oxygen and some of it's on the other oxygen. Those two atoms share the minus charge, whereas in, I'll even write that down, this is a delocalized minus charge. And again, it's what we said before. Anything you can do to spread out that negative charge over a larger surface area will mean less electron-electron repulsion. So I'll say delocalized minus charge. Whereas over on this alkoxide ion, this now is the conjugate base of the alcohol, that minus charge is localized on that oxygen. It's just sitting on that one atom. Nothing else is helping that oxygen to bear the minus charge. Now, that being said, in all fairness, if you're gonna put a minus charge on an atom, oxygen is one of your best choices to do that with, because oxygen's extremely electronegative. So we're certainly better off putting that minus charge on an oxygen than, say, on a nitrogen or a carbon. Right, but this is still going to be a less stable species than this one, because here, not only are we putting the minus charges on electronegative oxygens, we're also spreading out that minus charge over a larger surface area, which leads to less electron-electron repulsion, and means that in comparing these two species that otherwise are pretty similar, they have the same number of carbons, this is why we find that this conjugate base is more stable than this one. And since this conjugate base is more stable, well, I'll talk about that in a moment. But remember, the electrons are more near the atom where hydrogen is departing, then it will have more potential to attract that hydrogen back. I'm being picky here, but replace hydrogen with proton, H+. And then I think that that's probably true. That's probably right about what I'm about to say. So what does it mean? If this species is more stable than this one, that means this acid is much happier about giving up the proton, since it makes a more stable conjugate base, than this one is. And there are certainly bases that are strong enough to deprotonate an alcohol. It takes a pretty strong base. You're going to need at least like the conjugate base of ammonia, let's say, NH2-, or perhaps a carbanion, you know, CH3- or something like that, will be a strong enough base to deprotonate. Or what about hydride ion, H-, right? Those are two species to familiarize yourself with. This is the hydride ion. That's the conjugate base of hydrogen gas. That is not the same thing as H+, the proton. Very different critter, right? Because here this is hydrogen with a lone pair of electrons. But hydride ion is a very strong base, as you would expect. It's the conjugate base of H2, right? That's not exactly on the list of strong acids, quite the opposite. But there are hydride reagents that you can use, and those surely would deprotonate an alcohol, no problem. And we learned another way to protonate an alcohol, though that's not, technically that's not done as an acid-base reaction, that's a redox reaction. We said that you can add sodium metal or lithium metal or some other alkali metal to the alcohol, and then it will undergo a redox reaction. So it's not a base pulling the proton off, it's not the same thing. Instead, the hydrogen gets, let me get this right now, reduced from +1 to 0, while the alkali metal gets oxidized from 0 to +1 and goes into its cation state. So that will also work. There's many ways of deprotonating alcohols. But my point is, since carboxylic acids are much stronger acids, you don't need to go nearly as far to pull that proton off. H+ is no electrons. Yes, that's correct. That's why we call these protons, because the nucleus is literally a proton and nothing else. So hydride anion, that's an anion. And that's hydrogen in the rare -1 oxidation state. Generally, when hydrogen's combined with other elements, it's in the +1 oxidation state. But hydrides are known. It's generally the oxidation state of hydrogen you get when you combine hydrogen with metals. So you can get, for instance, sodium hydride or calcium hydride. You can get these things. And any of those I would expect would also be more than strong enough bases to deprotonate an alcohol. But you don't need to go nearly that far with carboxylic acids. You know, with this being some trillion times more acidic than a similar alcohol, you don't even need to go as far as sodium hydroxide, although sodium hydroxide will surely deprotonate a carboxylic acid. Considerably weaker bases will also do the trick. How about the bicarbonate ion, HCO3-? The bicarbonate ion is the conjugate base of carbonic acid, H2CO3. And I should have it at least a little bit memorized than this. But I think if you looked up the pK of carbonic acid, it would be quite a bit lower than that of water or alcohols. I think you'd find it to be round and about in the 8 to 9 area. Now someone's going to look it up on the internet for me and prove me wrong, which I'm okay with that. But I know you'll find it's a significantly stronger acid than water or alcohols. But bicarbonate ion is a more than strong enough base to pull the proton off. And you know this if you've ever mixed baking soda and vinegar. Vinegar has acetic acid in it to the tune of about 4 or 5%. So R is CH3 in acetic acid, of course. And baking soda is nothing other than sodium bicarbonate, NaHCO3. And so these two things react. This will pull a proton off of the carboxylic acid, and you get H2CO3, carbonic acid. Carbonic acid turns out to be quite unstable and readily breaks up to form CO2 and water. And that's the gas bubbles that you see. Those are carbon dioxide gas. And by the way, while we're on carbonic acid and bicarbonate and CO2 and all that, a rather complicated equilibrium amongst all of those species, H2CO3, HCO3-, CO3-2-, H2O and carbon dioxide, and there's a complicated equilibrium involving all of those guys where? In our lungs, of course. That's why we breathe out CO2. So, but all those things are going back and forth pretty rapidly amongst each other, with, of course, CO2 being formed as we exhale. And so the equilibrium will eventually be driven in that direction. But my point being, that's not an unimportant equilibrium. But even putting all that aside, my point here mainly is that you don't need to go nearly as far to deprotonate a carboxylic acid than to deprotonate an alcohol. Bicarbonate ion wouldn't come nowhere near deprotonating an alcohol. Even OH-, the conjugate base of water, might deprotonate a few alcohol molecules, but nothing nearly quantitative. So you need pretty strong bases to deprotonate alcohols. You do not need that for carboxylic acids. And I feel like I probably spent way too much time on that. But that's okay, we had fun. Let me just make sure I'm not missing anything. Oh, while we're talking about effective structure on acidity, just so you can see what I mean, let's make another comparison. So here's acetic acid. As I recall, its pKa is around and about 4 3/4. But what would happen if one by one, these 3 hydrogens on the methyl group, we replace them with chlorines? Chlorine is again quite electronegative. And someone was asking about the inductive effect before. And again, in all of these cases, we need to be thinking of the conjugate bases of these acids. So I'm going to push you, I'm going to make you imagine those on your own. But you know, the conjugate base of acetic acid is going to be CH3CO2-, with the CO2- group looking like this. Same thing with chloroacetic acid. And let's say we did that again. Cl2CHCO2H. And then last but not least, let's consider trichloroacetic acid. Cl3C, CO2H. And I will be honest, I don't have these other pKa's memorized, but as my old friend and now colleague, Dr. Jim Pennington would say, if only there were a way to look up something like that. So let's look it up. Chloroacetic acid. There you go, 1.25. So, you know, over 3 orders of magnitude, over 1,000 times more acidic. Let's do dichloroacetic acid. Wait a minute. How can they both be 1.25? Oh, okay. I was reading it wrong. Chloroacetic acid is 2.87. That makes a little more sense. So this is 1.25. This is not 1.25. This is 2.87. And of course, it probably doesn't need to be said, but of course I don't expect you to memorize these things. You see, I didn't have them memorized. So let's see. This is going to be about 100 times as acidic as acetic acid, and this almost 100 times more acidic still. So I would expect trichloroacetic acid to be right about 0, actually. Let's see. There we go, 0.77. Okay, so there's our answer. In any case, you can see that the pKa gets lower and lower as we replace H's with electronegative chlorines. That's because, again, if you imagine the conjugate bases, which one is the most acidic? Well, you guys tell me. Remember that on the pKa scale, the lower the pKa, the more acidic, the higher the pKa, the less acidic. So as we're replacing hydrogens with electronegative chlorine atoms, what we're doing is we're making the compound more and more acidic as we do that. And that's because, again, if you imagine these conjugate bases, sort of like we did up here, so CH3CO2-, ClCH2CO2-, as we're putting on more and more electronegative chlorine atoms, those chlorines are helping to bear that minus charge. They're sucking that electron density towards the electronegative chlorine atoms and spreading out that negative charge. So once again, you're getting less and less electron repulsion as you go. And so that's why you see this. Now, this certainly doesn't appear to be anything like linear. I don't think we learn too much by plotting a graph here, but I think we can make some sense as to why the pKa gets lower and lower as you replace hydrogens with more electronegative chlorine atoms. All this is to say that structural effects on acidity are common, and they can usually be explained by resonance or the inductive effect. In this case, it's going to be the inductive effect, because you're withdrawing more of the electron density away from that carboxylate group towards those electronegative chlorine atoms. And of course, I don't expect you to memorize these pKa's. That's not the point here. But I think being given them, we can make some sense of why we have this type of trend of lower and lower pKa's as we attach more electronegative atoms. That's really the main point I wanted to make here. Good. Let's see. Trying to think, I got about 6 minutes. So valence electrons are what makes the atom more electronegative. No, I think it's more a fundamental property of the atom itself. That's actually, I don't really know, I guess. Well, I don't think it can be completely that, because electronegativity also increases up the periodic table. And fluorine, chlorine, bromine, iodine, all of 7 valence electrons. So I mean, there might be some relationship, but it seems to me there's something else going on there. I'm not sure we really understand the fundamental physical principle that brings about more or less electronegativity. But just based on that, my guess would be that it might have something to do with the number of valence electrons, but something else is in play here too, I think. So that being said, our next topic, which we're not going to finish today, but I think we can at least start it, is considering how do we make carboxylic acids, preparation of carboxylic acids. And I think we already know a couple ways. We already know that you can oxidize either a primary alcohol or an aldehyde . Here's my aldehyde to a carboxylic acid by using nasty, extremely reactive transition metal reagents with highly, highly oxidized transition metals. So Jones reagent would do the job here for us. It's basically chromic acid. But I would expect the permanganate ion to do it as well, MnO4-, that's manganese in the +7 oxidation state. So there are others as well. There's other chromium reagents also, besides the Jones reagent. But any really powerful oxidizing agent, generally involving chromium or manganese in a really high oxidation state, will do that for us. And so the reason we're mentioning this is a way that we know how to make carboxylic acids. We can make it by oxidizing a primary alcohol or an aldehyde. And Jones reagent is just one of several reagents that will do that for us. Let's see. I think I'll also let you guys know, and this will at least get us through 10-7 mostly. We can always start here again on Friday. Let me actually do it like this. If we know of some way, can we also make carboxylic acids from esters as well? Yes, you can hydrolyze the ester, and we'll learn how to do that. However, that's usually you're doing the opposite. Usually one makes esters from carboxylic acids, and we'll get to that reaction probably on Friday. But there's another way of making carboxylic acids from nitriles, which is a good reason that they're mentioned in this chapter. And that is done by acid catalyzed hydrolysis. So we'll just use dilute aqueous acid. We'll just write H3O+. And remember, when you see H3O+, that implies that H2O is also present. This is a dilute solution of some inorganic acid in water. You can just take water and add some drops of concentrated sulfuric acid, for instance, or concentrated HCl. And in the end, you do get the carboxylic acid that has the same number of carbons, so the corresponding carboxylic acid. And all of these oxygens come from the water. And by the way, the nitrogen winds up in a molecule of ammonia. So it doesn't just disappear. It winds up in, or actually, since we're an acid, it would be in an NH4 plus ion, right? Doesn't really matter. That's going to be an inorganic side product. But if you heat a nitrile in dilute aqueous acid, you can hydrolyze the nitrile just as you can hydrolyze an ester, and you will get the carboxylic acid out of that. And again, you're not responsible for these mechanisms. They're very, very, very long, very steppy. What about nitriles? Do we know how to make those? Well, I think we maybe do. I think if we start with an alkyl halide, we know that you can have that undergo an SN2 reaction. Maybe treat this with sodium cyanide in DMSO or some other solvent like that, and this will undergo an SN2 reaction. So one thing I did in your class notes, but I haven't done here on this page, is to remind you of where you can review those reactions. So you can review this in section 6.4. That's where we talked about that. You can review these reactions in 7.12 and 9.13 if you've forgotten about those. And this actually is kind of a new reaction for us, the hydrolysis of nitriles. That's a kind of nucleophilic acyl substitution reaction. So we'll get to that in this chapter. We'll learn more hydrolysis reactions like that, but this works as well. And again, the nitrogen winds up in a molecule of ammonia effectively. So that's a reasonably good place to stop. I will just mention, these are just two of the ways of making carboxylic acids that are mentioned in 10.7. The others, if you look at the front, you'll see that I specifically said you're not responsible for those. So I think these are enough since it's largely familiar chemistry to us as well. Good, but I'm out of time, so I will leave it there, and I will see you all on Friday.